All right, so now we are going to look at a different. So far, starting with the sample mean, what we were looking at is what we were trying to measure was measuring the central tendency of the data, right? We were trying to find a typical data value, right? We were trying to find a value that is that represents a typical value of the data set. So the sample mean, the sample median, right, and so on. Everybody is clear on that? Now, think about, now what we want to do is we want to find a measure of dispersion. And I'm going to explain that in a bit, what is the meaning of that. Think about these three data sets. The first data set, D1, has only one value, 0. The second data set has two observations, -10 and 10. And the last data set has three observations. No, not three, sorry. Two observations again, -100 and +100. If you look at the mean for each one of them, what do you get? What's the mean of the first data set? What's the mean here? What's the mean of the second one? What's the mean? 0 and they all have the same mean, right? So how would you differentiate among the three data sets? Obviously, they are these three data sets are quite different, right? So the sample mean by itself isn't enough to summarize the data. Is that making sense? The sample mean or the median isn't enough to summarize the data that I have here. Okay? So clearly, what is the difference here? Well, the difference is in dispersion. Okay? That is, the difference is the distances among the observations, right? If you look at the distances among the observations, that's where they differ, right? So if you look at the distance among the observations in the first one, second one, and the third one, they are quite different. So what we want to do now is measure the dispersion of the observations, okay? So how are we going to do that? Well, one idea would be look at the average distance from the observations to the sample mean. Okay? Look at the average distance from the observations to the sample mean. So I have the number line here, and I plotted the sample mean x bar there, and then I have the observations labeled as x1, x2, xi, x21, xn. So I'm just trying to show you that you have these observations. So when I'm saying distance, right? What do I mean? What's the distance between xi and x bar? The distance between xi and x bar is that, right? Now I can just say the distance. Let's just say the distance is xi minus x bar, right? And so one idea would be to look at the average distance from the observations to the mean, which means that what I'm saying is that from each observation xi, you subtract the sample mean, right? And you sum over all values of I, right? Is that making sense? and then I divide by n, let's say. So xi minus x bar is called a deviation. Xi minus x bar is called the deviation of xi from x bar. Okay? So we are taking the average of the deviations. Right? Is that a good measure for the dispersion? Well, the problem here is this is going to be 0 no matter what observations you have. This quantity will always be 0. Is that making sense? Let me expand that. So basically that sum is always going to be 0. So if I am writing x1 minus x bar plus x2 minus x bar plus dot 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 plus xi minus x bar plus dot 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 plus xn minus x bar. What I'm saying is that this sum will always going to be 0. Okay? Why is that the case? Well, let's check. Let's check. I going from 1 up to n, xi minus x bar. Okay, that sum, I want to check that that's 0. Well, this is equal to the summation I going from 1 up to n of xi minus the summation I going from 1 up to n of x bar, right? If I have a sum, the summation symbol can be, summation can be taken term by term, right? Just like integrals. So if I could do that now, if you think about this, this is equal to the summation I going from 1 up to n xi. Now x bar is a constant number, right? It doesn't depend on I. So how many summands do I have in the second sum? In the second sum I have n summands and each one of them is x bar. So the second sum is simply n times x bar, you agree? N summands, each one of them is x bar. Well, this is equal to the summation I going from 1 up to n of xi minus n times, what is x bar? What's the formula for x bar? It is x1 plus x2 plus dot 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 plus xn over n, right? Well, n cancels out. If I cancel out n, what I get is the following. Well, x1 plus x2 plus dot 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 xn is left. So what is that? That's the same as the summation of xi I going from 1 up to n, right? The numerator there, in the second term, the numerator is the same as the summation of xi I going from 1 up to n, right? Well, what is that? That's 0. Okay, so what I'm then saying is that my first idea, the first idea that I had for measuring dispersion is not a good one. Okay? Because this is going to be, so remember I was trying to measure dispersion by this quantity here, and what I found is that this is always 0, so it's not gonna say much about the data. about the differences between data sets. So what would be my next idea? My next idea would be, let's say, the second idea, let's say, you know what, I have to create some space here. Let me know if you need me to stop to give you some time to write stuff down. Okay, so my second idea would be, well, instead of looking at just the deviations, why don't we look at absolute values of the deviations? So instead, let's look at xi minus x bar. Remember, xi minus x bar is called the deviation of x bar from deviation of xi from x bar. So this is so why don't we look at the average of the absolute values of the deviations, right? Well, this is not going to be 0. This is not going to be 0. Obviously, because these are all positive numbers, right? Well, so this is a good measure, by the way. This is a very good measure. This is a good measure. The only problem is, anytime you have seen problems with absolute values in calculus, were you irritated by that? I know I was, right? Absolute values are algebraically hard to manipulate. Okay? Because of that, we are going to forget about this measure. Okay? So the measure that we are going to take is called the sample variance. So instead of looking at the average value of the absolute values of the deviations, what we're going to look at is the average value of the squared deviations. So notice that I have xi minus x bar, right? I call xi minus x bar the deviation of xi from x bar, and I'm taking the square of that. So I'm going to call that squared deviation of xi from x bar. So here what I'm doing is then I'm taking the average of the squared deviations, and we are calling that sample variance, and we are going to take that as a measure of the dispersion. Now, notice one thing though, that in my definition, I am not dividing by n. I am dividing by n minus 1. Right? Why is that the case? Okay, why is that the case? Well, for now, let me say the following. Remember this equation that I have here. Look at that equation. If you know the first n minus 1 values in that equation, if you know the first n minus 1 summons on the left hand side of that equation, the nth summand of the left hand side can be determined from those other summands, right? That is, the nth summand, I can solve for the nth summand of this equation in terms of the other summands, right? You agree with that? So what I'm saying is that the nth summand of the equation star is determined by the other summands, right? The nth summand on the left hand side is determined by the other n minus 1 summands on the left hand side, because I can solve for it in terms of the other summands, right? So imagine the following. you are picking a sample, right? You're picking a sample of size n. So think about x1. So you're picking the sample, it's picking the observations randomly, okay? So think of x1 as the value of your first observation, right? x2 is the value of your second pick, the value of your second observation. x3 is the value of your third observation, and so on. Notice that you can think of the first n-1 summons as could be anything, right? The values of the first n-1 summons could be anything, right? Could be random, because let's say I'm picking things randomly. While the last one is not going to be random, because the last one will be determined in terms of the other ones, okay? And that, because of that, n-1 is called the degrees of freedom. So the degrees of freedom, df, will be n-1 here, okay? There is n-1 degrees of freedom among these deviations, okay? I said squared deviation, so I have to put a square around it. Squared deviation of xi from the mean. Okay, so the sample variance can also be written, so I can do some algebraic manipulation here, which I'm not going to show you. If you are interested, you can do it yourself. Maybe it's a good homework to give you, or a good quiz, to show that the first equation for the sample variance is the same as what I have in my remark number 3. So the sample variance is also the summation of xi squared minus the summation of xi whole squared divided by n n-1. Now, can someone tell me what is the squared term I have? If you look at the second term in the numerator, right? Second term in the numerator, I am taking the summation of the observations first, and then I'm taking the square. Are we okay with that? Okay. Now, why do I care about the second formula for the variance? Because when you try to compute variance, the second one is easier to use, because the second one is basically in terms of the observations, right? So I'll show you next time how to calculate sample variance from a table of observations, okay?